Alrighty, welcome back to the C++ course. This is chapter 13, where we'll be talking about advanced file and I/O operations. So a lot more information about getting data out of external files and getting data into external files. Here's our list of topics. So we're going to take another look at input and output streams, hence I/O stream, more detailed error testing, member functions for reading and writing files, so some sort of built-in functionality built into C++, the language for dealing with file I/O. We'll take a look at a different kind of file called binary files. So far we've just been dealing with ASCII files. We're going to take a look at records, structures, random access in files, and opening a file for both input and output. I should mention before we get started, this particular chapter involves a lot of, as you probably can guess, external assets. So I've gone ahead and put the textbook files on the Canvas files section. You'll find it under Files and then Chapter Source Code Listing, and then just go to Chapter 13. If you're online on YouTube, you'll find a link to these resources in the video description. Here's what it kind of looks like. I've just got the Chapter 13 textbook files open, just kind of hanging out over here. We'll go ahead and copy these files into our project directory as we need them. We won't need them all, and in fact, you'll notice that you do get access to all the example files scattered throughout the chapters. So if we either skip over some or go too fast, you can always refer back to these finished versions of the source code listings in the chapter. And I'd highly recommend you do so, especially for the ones that we either do like a read-only of or just skip over entirely. So keep these external files handy as we start chapter 13. So input and output streams, data streams from which information can be read. That is an input stream. We've already seen an example of this many times called cin in the keyboard. We can use iStream, ifstream, and iStringStream objects to read data. And then for putting data out to streams, we can write data to them with like cout, ostream, ofstream, and ostringstream, again, to write the data. Now for I/O streams, for both combined data streams that can be both read from and written to, you can use fstream for these. I should mention that the techniques that we use here in C++ for file I/O basically translate very nicely to other programming languages. Most languages support this type of file I/O. It's a very common thing to do. For example, just one off the top of my head, in like 2D game design, you would use this technique when creating like your top-down tile map or even your side view tile maps, where you have rows and columns of tiles, many images basically, and then you could specify in an external file like ones and zeros, basically defining what your map is going to look like, where a 1 represents this kind of tile, a 0 represents this kind of tile, or even 3, 4, 5 all represent different types of tiles that can be used and displayed in your maps. So again, needless to say, these techniques are incredibly useful. File stream classes. So ifstream, open primarily for input, and ofstream primarily for output, and fstream is for both. So these are the big hitters here when we're talking about file I/O. They all have initialization constructors that take a file name as a C string. So here we go, call back to last chapter, dealing with C strings. They want that old school representation of a string. But in newer versions of C++, you can pass in just a string object. And it's important that we use close to disconnect the program from an external file when access is no longer needed, so that our computer, the operating system, doesn't think that our program is like trying to read or write from a file. This also kind of pops up if you have the file open, like if I went to my list of external assets here and I just opened addresses.txt and I was just editing it in Notepad or something, and then I kept it open, but then I ran my program that needed that file, you may run into trouble because the operating system has that file kind of locked. As I'm editing it in Notepad, my program can't also make changes to it. Now that's dependent on some different variables, but if you run into it, just know that you need to have, in general, your files closed for your programs, your C++ programs, to read and write to them. Keep that in mind. And we're going to make sure we stay nice and tidy, and when we're done dealing with the external files that we're reading and writing to, we're going to use close to free that up so that other resources on our operating system can work with them. Files should only be open while being used. Always close files before the program ends. Let's jump into 13.1, page 869. And this is going to be just a good kind of, I guess, level setting kind of program where we're just going to make sure that we can access these external assets and make sure that we put our files in the right spot. I've already kind of got a project queued up here. We'll create this. And we've got our IO stream. We'll include fstream and good old string. Using the standard namespace. And we will create an fstream object. Fstream in out file string word. We'll open the file. So in out file dot open. Pass in the name of the file that we want to open, which is called in out.txt. Now let's see if we can put that in the correct location. I'm going to kind of guess here. It's a little bit different environment to environment. In a Visual Studio, we have to figure out, and you guys probably have this figured out better than I because you have some assignments that required this, trying to figure out where we want to put in-out.txt. And I struggle with this even in real world programming projects that I work on professionally, which is where do we want to put these external assets? Let's just try to put it in the source files. So let's remind ourselves of where we have these files stored. Mine is in a junk folder, grading, not that your grading is junk. That's more like a temp folder. Junk grading source code. Okay. Here's my junk grading source code, chapter 13, and it is called in-out.txt. And if you're curious how I did that, that was a right click on the folder, add existing item. Since the file already exists, kind of just copied it in there. Now right away I've opened it. I'm going to do an in-out file dot close down. And let's see what we're going to do in between. So we've got it open. If in-out file dot fail, this is just a check to make sure that we can open the file. We're going to print out an error. The file was not found. Instead of crashing, we'll kind of fail gracefully here. So we'll end line, and then we will return. So notice how we're returning a code other than 0. We're going to use this to basically simulate the fact that this program did not finish running successfully. Now let's read in. So while in out file reading into the word variable, the word string. While we're doing that, we're just going to cout word, cout endl. Now we'll say in out file dot clear the end of the file flag to allow additional file operations. We will now write to the file in out file dot angle bracket hello, and then an end line. Now notice the end line. We're not couting here. We're like using those angle brackets in the context of our in-out file. So keep that endl in the back of your mind. Then we close and all is well. Now the true test, this kind of sanity check, we're going to try to run the program and make sure that we can open in-out.txt. File's not found. So it has not been found. So you can see that hopefully that's a little bit nicer than just throwing up a runtime error and just crashing very, very ungracefully. We caught that error here kind of with just a manual if statement check. And in some sense, that's better than just crumbling to the ground. But the question remains, where are we going to put it? Well, I stopped the recording and I resumed it again, and it turns out that we need to copy our external files in the project folder. So chapter 13, this is kind of my solution folder. Here's my program folder, my project level folder, 13-1. We'll copy and paste inout.txt so that it's right next to my Visual Studio project file. So right here, right within the project folder. And that should do it. Now we've got hello, hello. See it twice because I already ran it once. You guys didn't see that, but it's been written twice now. Now let's just check something. I want to open that file. Whoops, not that one. I want to open my project folder. Right here, inout.txt. Let's take a peek at it. I'll just edit it. And you can see now it's 3 times. And there's my little endl. That little thing I told you not to forget about. Keep it in the back of your mind. This endl is what gives us this extra blank line at the end. Okay, we got all the kinks worked out. Hopefully the rest of the lesson will go a little bit more smoothly, but you can see we were able to use the while loop to get everything out of the file. We cleared out the end of file marker, and then we wrote a little bit of information to the file. We closed it up and freed it up for whatever else may need to use it. Okay, kinks worked out. File open modes. They specify how a file is opened and how it can be used once it is open. And here's an example. So basically iOS scope resolution in, iOS, not Apple iOS, input output stream in, input output stream out are examples of file open modes and also called the file mode flag. These modes can be combined and passed as second arguments of the open member function. Let's check out 13-2. And we'll do another hands-on here. Again, hopefully these go a little bit more smoothly this time. Console app. IOmanip. I'm going to include that guy and include sstream. I will caution you, sometimes the hands-on slides don't align perfectly for where we are in the chapter, so just a fair warning there. We are going to take a look at how to use the OString stream object to do sophisticated formatting. So not necessarily related to file open modes here, but a good example nonetheless. So let's delete that. Let's using std. And even outside of main here, we have a function that's going to return a string called $format. We looked at something kind of like this last chapter, actually. It's going to pass in a double. Inside of main, we'll create a const int rows equals 3, calls equals 2. Double amount, we're going to create a 2D array here, rows and calls equals some data, 184.45, 759.13, 64.32, 7.29, and 1289. All right, format the table of dollar amounts, right justified in columns of width 10. So some good old output formatting here. All right, let's see out. That's my wonderful IOmanip library in action. For int row equals 0, row is less than rows. Yes, row is less than rows, row plus plus. Your classic 2 levels deep for loop here, iterating through a 2-dimensional array. For int column equals 0, column is less than calls, column plus plus. And we will say cout, yeah, sure, set width 10, and then we'll print out the result of a call to $format, passing in the amount array at location row column, that two-dimensional array access. And that's good. After the inner for loop, we're going to cout an endl, just for a little extra formatting. And now outside of main, we are going to implement our function string $format, passing in a double called amount. We'll create an ostring stream object called outstr. Then it says set up format information and write to the outstring. So outstr show point fixed and set precision of 2. Outstr print a $char followed by the amount. We'll return outstr.str, whatever that is, return its string equivalent. Do I see any? Yeah, I don't see any external files in here. Let's just run it. Cool. So what is the point of this? The point is we're able to use these angle brackets with things other than cout. So it's more or less just trying to show you that, hey, you can write to stuff other than cout. It turns out here that that's exactly what you're doing, but really all we have been doing so far is printing to cout, reading in from cin, and a little bit of file IO earlier on, but definitely primarily cout and cin. So this is just showing that we can use some extra, we can use the syntax in ways other than those, so other than cout, cin. Let's check out 13.3 right here. Demonstrates input and output of numbers using octal, decimal, hexadecimal number systems. This is kind of cool. We'll just read through it here. So we've got two ints, A, B. We're going to read two decimals and print their hex and octal equivalents. So enter two decimal numbers, give me an A, give me a B. The numbers in decimal are whatever they are, just print them out. That's nothing remarkable, nothing new. The number in hexadecimal, though, you're changing, when you do this and then say hex, you're changing kind of the mode of output. Then you're saying show base, then show me the data, followed by a tab, and then the data again. Then you can show the numbers in octal, and then you say output, output, or angle bracket, oct. You're sort of shifting modes there. You were in decimal by default, and then you were in hex. Now you're changing the mode to octal, printing it out. Then we're going to read some hexadecimal and print their decimal equivalents. Oh my. Okay, so enter two hexadecimal numbers. And by the way, if you want to play with this and verify it, just pulling up the good old Windows calculator, changing your mode to programmer will allow you to compute and calculate in any of these modes. Hexadecimal, decimal, the default, octal, and then binary if you want to see the ones and zeros behind the scenes. So feel free to play with this a little bit if you'd like to prove what we're doing here in our programs. All right, so reading in, we're kind of doing the same way. So we enter two hexadecimal numbers, we're doing cin, then we're changing the mode to hex. Then we're reading in an A, reading in a B. You entered the decimal, change mode to decimal, print out A and a tab and a B. Then read some octals, so cout, cin, change your mode to octal, read in A and a B, and then print out those decimal versions. Kind of interesting. Sample run of the program might look like this. Enter two decimals, 23 and 45. Print out 23, 45. In hexadecimal, those values are 17. I should say 17 and then 2D. We can verify that. Remember, the 0x is not part of the hex value. That is a symbol to indicate that the data that you're seeing here is hexadecimal. Show you how to run that. We're in decimal mode. If we just hit 23 and then shift over to hexadecimal, sure enough, it's 17. Clear this. If we enter 45, shift over to hex 2D. Cool. and then the rest, shifting between those modes there. Okay, fstream can be used for either input or output. As we've seen, we create a file object, an fstream file object. To use fstream for input, we specify iOS scope resolution in as the second argument, so that might look like this. We've seen file.open, where we specify the name of the file. Then, as an argument, we say, comma, the mode that we want to work in. To use it as output, specify iOS : out, like this. Here's some other flags for manipulating files. So if you pass in this flag, you'll create a new or append to the end of an existing file. That's interesting, because if you go to file.open, a file name that doesn't exist on your hard drive, it'll be created. If it does exist, you'll be appending to the end of the existing file. iOS 8, go to the end of the existing file and write anywhere. Binary, you're reading and writing in binary mode. So hexadecimal 45, binary mode is a bunch of ones and zeros, sort of. Yeah, kind of. Think of it like that. Passing in an in, you're opening for input, out for output, and then trunc is kind of dangerous. Open for output, erase, and truncates the file if it exists. Use with caution. Like we've been saying, fstream can be used for both I and O at the same time. So you create the fstream object and specify both as the second argument in the open member function or the constructor. And this is what that looks like. This is called a pipe, or a vertical bar, mostly called pipe. It's the same character that we use two of when we want to say or, only here it's how we can specify two modes that we want to work with in file.open. Again, called the vertical pipe. 13.4.877. Let's do it. Include fstream, iostream, standard namespace. Do we need any files? We need good old stuff.dat. So let's bring in stuff.dat. I don't know why I can't get at my file explorer here. Let me move it over. Nope. Okay, fine. Chapter 13, stuff.dat. Right? And remember, the file extension is largely irrelevant. The file extension is important to Windows so that when you double-click the file, it knows what app to open the file with. But in our case, we have a DAT extension, so it doesn't know. We could hit open with and find good old Notepad, and we would see that it's really just data. Like it could have just as easily been stuff.txt, but just to show you that it doesn't matter, it's the contents that matters. They just renamed it .dat. Okay, so we got our stuff ready. Fstream test file stuff.dat. We're going to open it in iOS out mode. If test file dot epic fail can't open file, int num equals 10, cout writing to the file, test file, angle bracket, followed by num. So we're writing 10 to the file. And we've got some function here called, I missed this prototype above, called show state. That's going to accept test file as an argument. And we'll say test file dot close. Now I don't like that red squiggly, and we do have a prototype up there that I missed. So void show state just accepts an fstream object address. Cool. That gets rid of my squiggly at least. Obviously we haven't implemented the function, but at least Visual Studio is not complaining to me anymore. We've closed it up. Let's open it and open it to read. Yes, so test file.open stuff.dat iOS in if again test file dot fail can't open return 0. Cout reading from file test file num. Right. Do we make that? Wait a minute. Test file out angle bracket num. That's good. Show state. Yes. Down here, reading from the file. I think I had that backwards. Num. Show state. So that show state function is just to basically show what we've done to test file as we're doing it. So we don't have to write all that code more than once. Forcing a bad read operation. Test file num. Show state test file. Let's close it up. Return 0. We do have show state that we need to write. Yeah, not too big of a deal here. Okay. Void show state fstream reference called file cout file status cout EOF bit and a file bit is what that is called. File.eof. Show me what that is. Followed by an endl. There we go. Cout fail bit. Show me the bad bit. Finally, clear it and clear out any bad bits. All right. Let's make sure we can activate this. Right, and run it. And hopefully it can see that file there. Problems. Oh, parens. All right, so we have a fail bit here. I guess maybe first of all we should have seen what exactly is in that file. We saw it was a 1 and a 0, if I'm not mistaken. Let's just double check that. I opened it, but I was not paying attention. Yes, a 1 and a 0. And it says down here, for the purpose of error testing, a stream object behaves as a Boolean expression that, if true, has no error flag set and false otherwise. Check whether the last operation is valid or has succeeded. You can just say this instead of checking the fail. You could, though. Cool. All right, opening files with constructors. So stream constructors have overloaded versions that take the same params as open. The constructors open the file, eliminating the need for a separate call to open. So we basically, like it says, treated those as separate lines. So we combine these all in once. We we don't have to declare it first and then call open. We can just do it all inlined in the constructor. Again, ifstream, ofstream, and fstream have default open modes defined for them, hence the second parameter to their open member function is optional. When we first used these, we didn't pass in any modes, and it worked just fine, because it turns out that they all have defaults. So ifstream opens for input, OF open for output, and fstream does both. All right, let's read through this guy. We're including IOStream, string, and fstream. We've got an fstream object called file and a string for the input. We'll open the file, opening it in input mode. If it can't, fail. So this is the same thing as saying, back over here, calling the fail method on it. We can just say if not file, return there's a problem, read the file in and echo it to the screen. So if you're not failed, see out the input to the file, close it up, and we return. And apparently, whatever file, murphy.txt, this is, I guess, what is contained in it. All right. Output formatting with IO manipulators can format with IO manips. They work with file objects like they work with cout. We saw this example a little bit earlier. You can format with formatting member functions. The ostring_stream class allows in-memory formatting into a string object before you actually write it to the file. And here's what we, again, already kind of saw. So you can justify left or right the output. It's just like working in Microsoft Word. Maybe not. You can change, like we saw, your format of your data from octal to decimal to hex. You can write a new line and flush the output with these two. You can do or do not show plus with non-negative numbers. So that's like if you have a positive value, it will show a plus sign. Just like if you have a negative number, it'll show the minus sign. And then you can show or not show decimal points and trailing zeros. Fixed or scientific, you can switch between those modes. Set width, we saw many chapters ago, sets the minimum field output width. You can set your precision, set your fill. To format output into an in-memory string object, you include the sstream header file and create an ostring_stream object like so. So in this case, you're not like writing it to the file right away. You're basically creating an in-memory string that you're formatting with the understanding that you will be sending it to some kind of file output later. At least that's how I think of it. Write to the ostring_stream output using IO manips and all their stream member functions, like so. Again, we've already kind of seen an example of this. You're saying outstring, then changing modes to show point, changing your mode to fixed, setting your precision, printing a $sign, and then whatever value amount contains. You can access the C string inside the ostring_stream object by calling its str member function. So out_str.str will get you that C string if you need it for some call. I should say if you need it as a parameter to a call to some other function. If that function requires a C string, you can get at it very easily by calling .str on any string. All right. More error testing. So stream objects have error flags, or bit error flags, that are set by every operation to indicate yes or no, I succeeded or I failed, and the status of the stream. And member functions report on the settings of the flags. Here's kind of what we saw in that last example, a couple examples ago, a little bit better explained. End of file bit. So you examine the error state bits to determine the status of the stream. The EOF bit is set when the end of file is detected. The fail bit is when any operation fails. A hard fail is when you fail and you cannot recover. A bad bit is when an invalid operation is attempted, and good bit is set when no other bits are set. Basically just, like we say, little status flags telling you what's going on as you're reading and writing two files. You can use these functions like we saw earlier. EOF is true if the EOF bit is set, otherwise it's false. You can use the fail to check the fail bit or hard fail bit. You can use .bad to see if the bad bit, likewise good, if good bit. And you can clear all the flags down here or clear a specific flag. So the file stream is set to true if a file operation succeeds, and it's false if it fails. You can test any status of the stream by testing the file handle. So like this, as we saw in the example to the right here. If not in file means it couldn't be opened. And here's another way to get out of a program. I don't know that we've seen this yet before. Like in our examples, we were just returning other values. You can also use this exit built-in C++ function to exit your program in a variety of ways. In this case, they're passing some status code 1 to exit, and that presumably means something to the programmer writing the code. It can mean whatever they want it to mean. Member functions for reading and writing files. Okay, so unlike the extraction operator, that's the name of that thing. I've just been saying angle brackets, but it does have a technical sounding name, the extraction operator. I'm fine if you just want to call it angle brackets. These reading functions do not skip white space. So getLine reads a line of input. Get and peek read a single character. Seek G goes to a location in the input file. Okay, so getLine. GetLine is a function that we call with a source, a dest, and a stop char. So the source is the stream being read from. The destination is the string to hold the text from the source. So as we're reading from the source, we have to put that data somewhere in our program. We're going to put it in the destination parameter. And then the stop char is the terminating character. Optional default is /newline. Okay, again, mentioned this last time when we talked about the null terminating character in a C-style string. That was a /0. Here we have a /n. It is treated as one character even though it's inside of single quotes. We're used to seeing single quoted characters as having like one thing between them. But in this case, it is still a character even though it has two symbols there. Okay, so it uses getLine to read a line of information from a file. We've got an F stream called the name file and a string input. So we're going to open the file murphy.txt in input mode. If it can't open, fail gracefully. Read the first lines via getLine. So we're reading from this F stream and we're placing what we've read into the input string. Now, while name of file, so while it's basically still got stuff to print, if successful, print the line and read another line. So terrible place to put it on two separate pages, I think, but we'll just try to remember on this previous page, it has while name of file. So while that is successful, print the line and read another. So this is just simply printing the line. Then we're going to get another line. Okay, get line, name of file, input. Read the file, put the data that you read into input. Do that as many times as you can until you fail. Once you do fail, close it up, return 0. Okay, file demonstrates getLine with a user-specified delimiter. So same kind of idea here. We've got a string for the input. We're going to open up our file in input mode, fail if it can't be opened. Then check this out. So read lines terminated by some arbitrary symbol, in this case the $, and output it. So get line from data file into input while you have, I should say, with the understanding that this is going to be our terminating character. Keep doing that until you can't anymore, close it up, return. So we don't always have to use the /n as our stop char. That's what this is saying. We can use a $sign in its place. So if getLine gets us a single line, get is a way to get a single character of input. So read a single character from input stream and return the character does not skip white space. So remember, getLine does skip white space, get does not. So we create an input file stream called inFile and a simple char called ch. We're going to open up my file just to drive that previous point about file extensions home, you don't even need a file extension. You could just completely leave it off. Windows won't have a clue what to do with it if you were to double click it. It's going to ask you what application you want to use to open that file, but we don't care. In our programming, my file contains presumably some ASCII data, and that's all that matters. I just need to make sure if it truly does not have a file extension, that I don't put it here. And I would argue that best practice would be to give it some file extension, just anything really. TXT, DAT are good defaults, but you don't need it. All right, ch equals infile.get. It's going to get a single character from that input file stream, print it out, move on. You can also do it like this. So read a single character from the input stream and put it into char and does not skip white space. Yeah, so it's, try to point out the differences here. Here when we say infile.get, we're using ch. So ch equals infile.get. If that doesn't strike your fancy, it makes more sense syntactically, I guess, for you in your use case. You can do it like this. So infile.open, and then instead of using the equal sign, we just say infile.get and pass in that char that we want to put the data into, print it out, moving on. And here's a simple example on how to use get. Nothing terribly remarkable going on here, so we'll just kind of read it through. We've got our file name string, an fstream file, and a char called ch. So in this case, I guess there is one new thing going on in that we are prompting for the file name from the user. So in this case, the user is going to specify the file name themselves. So get me a file name from the user, then file.open it, and file.open wants that C string. So remember, file name is a string, but file.open wants a C string. So here's a good use case for .c string. iOS opening it in input mode, again failing gracefully. Ch equals file.get. While you haven't reached the end of file, that's what EOF means, print out the character and get another one. Eventually, as you loop through this thing, ch is going to equal end of file. When that happens, exit out of the while loop, close the file, and return. Okay, single character input with a difference. Peek. So what is peek? Read a single character from the input stream, but do not remove the character from the input stream. That's why it's peek. Does not skip white space. So it just looks ahead, basically, is how you can think of that. Again, we've got our input file stream, we've got our char. We're opening it up. We're saying ch equals infile.peek. If we print that ch, we're going to see whatever it is. And then if we peek again, we're going to get that same output because we're not actually, how I like to think of this is we're not actually processing the thing that we get. We're not like moving the stream forward. With get, we would get the character, and then if we called get again, we would move forward in the file. We'd move forward one character in the file and get the next one. Here, when we peek, we just look. We don't get it, but we look ahead. Okay, let's take a look at hands-on 13.9. Simple setup here, char ch and an int called number. So we're going to read characters and numbers, and we're going to take a look at how peek works. Okay, so we're actually going to be opening up two files here. So we're going to open the file to be modified and store that in file. So in file is the file that's modified, and then open the file to receive the modified copy. So we're opening two at the same time. No reason why we can't do that. We just have to make sure we remember to close them both at the end. So we're going to open the file to receive the modified copy. Keeping in mind here the modes that we're using. So the in file, we're opening it in input mode, and the output file, we're opening in output mode. Now we're going to copy the input file one character at a time, except numbers in the input file, and it must have one added to them. interesting, somewhat arbitrary way of modifying it, but that's okay. So we'll peek at the first character, and we're going to say ch equals infile.peek. Just take a look at it, and while ch has not equaled the end of file, check out the current character. So remember, ch is the peeked version of ch. If it is a digit, numbers should be read with that, by the way. We're going to use the angle brackets here, and in file, angle bracket number, and out file, we're going to write the number plus 1. Does that kind of make sense? We're going to get the character, if it is a number, place it into number, that's reading it in, then we're going to write out file, the value of number plus 1. If it's not a digit, it's just a simple character, read it and copy it. Then peek at the next one from the input file and check to see if it's end of file. If not, rinse and repeat until you're done, close both files and return. Single character output. Okay. Like get, we have put, and we can put a character. Outputs a character to a file, and the integer code of the character is passed to put. Like this, OFStream outfile.open, whatever your file name is, we can put a character to it. To copy an input file to an output file, which is kind of what we just saw over on the other side there, create a char, we can get a char. While the in file has not failed, we can put and get and then close. Okay, here's something interesting. Seek G. Offset, whoops. I actually don't know what the G stands for. Maybe we'll discover it together. Seek G takes an offset and a place. So you're moving to a given offset relative to a given place in the file. So this is a way to not have to start processing your files at the beginning and stopping at the end. It's more of where you're starting, I guess. So you can specify an offset of a given place, and that's where you want to start processing it. So the offset is the number of bytes from place specified as a long. So what is place? Place is like where you're starting, and then offset is how far you are from that starting point in the file. So place then is the location in the file from which to compute the offset. And you can keep bumping my scroll wheel. You can use things like beginning of the file, end of the file, and then cur, which is your current position in the file. Rewinding a file. To move to the beginning of a file, seek to an offset of 0 from the beginning. Okay, so if you want to process the file again for some reason, maybe you've done your while loop and you've processed it all, you've reached the end of file, maybe you want to do it again. So you can rewind to the beginning like this in file.seek. Here's your syntax for doing that. You have an error or EOF bit that will block seeking to the beginning of the file. Clear the bits first, then seek. And let's just check out 888. I want to re-emphasize that with this note here. If you're already at the end of the file, you must clear the end of file flag before calling this function. Thus, to move to the beginning of the file, stream data in, you have to just read to the end. You would have two statements. You clear it, then you seek to the beginning. Here's an example of how to rewind it. It creates a file, writes to it, closes the file. Then you open for input, read once to the end, rewind, then read again. That's not confusing at all. So shows how to rewind a file. So writes file, opens it for reading, then rewinds to the beginning and reads it again. I suppose in this day and age, rewind as a term doesn't make a ton of sense given that we don't have VHS tapes and cassette tapes to rewind really. We more like skip in today's era of DVDs, digital streaming, and MP3 music files, but use your imagination or look up on Wikipedia what VHS tapes and cassette tapes are. So here's how it works. Variables needed to read or write file one character at a time. A char called ch. We are opening this for output called rewind.txt. We'll open it, check to see if there's a problem. We'll write to it and close. So IO file, output all good dogs growl, bark, and eat. closed a file. Reopen it. Fail gracefully if it can't be reopened. Read the file and echo it to the stream. So we're just looping through it till it fails, putting it, getting it, putting it, getting it. Rewind the file. So remember the syntax for rewinding, we have to clear the error flags first. Then we can seek G to the beginning and then process again. Okay, so binary files. So we've been working primarily with ASCII type files or decimal type files, but binary. So binary files store data in the same format that a computer uses in main memory, whereas text files store data in which numeric values have been converted into strings of ASCII characters. So files are opened in text mode as text files by default. So what's like an example of a binary file? I mean, obviously we've seen text files like junk, grading. You know, we have TXT, we've got DAT, got some HTML, that counts too, I guess. Yeah, really just those are CPP files. Those are just text files. That's not binary. What is a binary file, or what would be a good example of that? Maybe if we go here, find a file, opening random images on my computer's hard drive, always good. Yeah, so here's a file called Even More Junk, no AI allowed, evenmorejunk.png. So what does that look like under the hood? Like, if I go to edit it, it opens it in Paint. What if I want to force it to open in Notepad++? Here it is. Okay, this is binary data. It's a bunch of gobbledygook that we don't really understand. But a computer does. A computer sees, well, this PNG and knows to open it in sort of your PNG viewer on your computer, but this is all binary data. It's just a bunch of junk. We don't understand, but a computer does. The computer uses it in main memory. So how do we use binary files? You pass the binary flag to the open member function to open a file in binary mode, like you see there. We can read and write binary using special read and write member functions. So we have to use a pointer to a char called buffer and then an int for the number of bytes we want to read or write. So here we're not dealing with like individual characters necessarily. We're dealing with bytes. How many bytes are we wanting to read and write from our binary file? So again, that's the signature. So buffer holds an array of bytes to transfer between memory and the file. So as you're processing this thing, you're storing the data that you want to read or write into this buffer before you actually put it there. The number of bytes is the number of bytes to transfer. So the address of the buffer may need to be cast to a char pointer using this funky syntax, reinterpret cast pointer to char. How do we use it? To write an array of 2 doubles to a binary file, you can do this. Same kind of syntax, opening it in binary mode, an array of 2 doubles. And to write it, what are we writing first of all? Okay, we're going to write in binary mode. What are we going to write? We're going to write this D, this double array of size 2. What are we writing? We're going to write, or I should say, how much are we writing? We're going to write the size of D, which is an array of 2. So that's nice because we don't need to specify, we don't have to like know how many bytes in particular we're writing. We can kind of fake it and you just use size of to figure that out for us. That's what it's there for. We don't need to know under the hood how many bytes a double is, or an int or a char. We don't need to have to know that. The computer knows that. It does a better job of it than we would. We'll just use size of and have it determined at, in this case, compile time, since that's a statically allocated array. Use size of, it's your friend. So read on the flip side. So if we wanted to read 2 doubles from a binary file into an array, we could do so like this. We've got our size, which is 10, a data array, size 10 doubles. And if we want to read it in, it looks like this. So what data are we reading? We're reading from the data array. We're taking this amount of bytes, 2 times whatever the size of a double is, bytes. And it just happens to say here that only data at location 0 and 1 can actually contain values. 894. Okay, this program uses write and read functions. Good enough. So file object used to access a file. So we've got an fstream object here called file reading and writing to nums.dat. And notice here we are chaining together these modes. So we're chaining together output mode and saying we want to open it in binary mode. Let's see, what are we doing? We're writing an integer array to write to the binary file. The size of the array that we want to write is the size of our buffer array divided by the size of whatever the size of buffer at index 0 is, whatever the size of my first element of that array is. Let me scroll this over. This note may be helpful. It might be useful to review this a little bit. Recall that the size of operator can be used on variables to determine the number of bytes occupied by the variable. Here, size of buffer returns the number of bytes allocated to the array by the initialization statement, and size of buffer 0 returns the number of bytes occupied by a single entry. By dividing the former by the latter, we obtain the number of array entries which we store in the size. The number of entries. Okay. And I may have misspoke there. Here, size isn't the number of bytes we're writing, it's the size of the array. It's just doing like a clever way to get at the size of the array. Now write the data and close the file. So write, again, we've got our funky cast here to a char pointer. We're writing our buffer and we're writing the size of that buffer. Pretty straightforward. Close it up. Open the file and use binary read to read the contents of the file into an array. Open it in input mode. Fail if it can't. Read into buffer using the size of the buffer. Then write it out. Write out what we just read into it, basically. So cout buffer at location count, while count is less than size. Yes, size is the number of elements in the array, not the number of bytes we want to write. Again, just a clever way, that division above is just a clever way of getting at the number of elements in your array. Big whoop. Stop trying to impress us, textbook. All right, creating records with structures. Shifting gears a little bit here, still dealing with I/O, but doing it in more of a structured way. If you haven't noticed, anytime we have to read and write to and from files, we kind of have to make up the format of the file ourselves and make sure that we enforce that format wherever we're operating on it within our code. Let me give you an example. Just pull up some sample file here. So it's called new4 whatever. It's an ASCII file. Say we're storing a bunch of information about players. So maybe we say, okay, here's my file. I have player 1 : high score. Player 2 : high score, which is something else. Okay, here I have this sort of self-imposed file format, I guess, where I know that each line of data in this file is going to contain 2 pieces of information. It's going to contain the player ID and the high score for that player, separated by a colon. Now maybe I want to take this a step further and provide even more data. Maybe I want to provide what level they are. Maybe he's level 9, she's level 10, he's level 11. Now I have more information and more structure imposed upon the individual lines of data in this file. I know the first piece of data is a player ID or player name, then the high score, then what level they're at. Okay, I impose that upon myself. I have to make sure that I enforce that whenever I'm reading and writing to and from this particular data file. Okay, so how does that relate to this? Well, let's see. You can write structures to and read structures from files. So just the very name of it, structuring this whole operation. To work with structures and files, use binary flag to open and read and write member functions. Okay, we've got records with structures. So remember back when we worked with the struct data type. So we're creating a struct here called test score. It contains the following data members: an int called student ID, a double called score, and a char called grade. We're creating an array of 20 of those test scores, and we can write out those to a file. So gradefile.write, and this is, we're going to see an example of this, I'm sure, but this is pretty cool if you think about it. So what we're doing is we're casting it, first of all, to a pointer to char. What are we writing? We're going to write out the test1 array. How many bytes is it? It is the size of our test1 array. I wish they would give us an example of output here, because we're just going to have to believe them that it worked, but let's check out a hands-on. I hope that, yeah, this is a good example. Let's do this one. Include fstream, include cstring, include cctype. As the listing mentions, this is for to upper. Using standard namespace, we've got some consts. Const int name size equals 51, addr size equals 51, phone size equals 14. Okay, we're going to create a struct here, struct info char, char array called name of size name size. Cool. An int age char address 1 addr size char array address 2, so we're giving the ability to provide 2 address lines, basically addr size, and then a char array called phone of size phone size. Very good. We've got our struct defined. Now let's see how we can use it to read and write. So let's create an info object here. Call it person, HR response. Create a string called input, and we'll rock and roll here. So fstream people, people.dat, using the iOS out and iOS binary. If not people, error, return 0. Let me check my folder of files here to see if they have something they want us to be working with the people.dat. Sure they do. Okay. Let's copy that and open this guy in File Explorer. Oops. Let's see what it looks like. Binary data, of course. So Abraham Lincoln, then who knows what. You can notice how you can kind of make out some of the data. Yeah, I can see his name. I can maybe see some address info, but there's a lot of nonsense in here. Maybe part of a phone number. Okay. I'm glad we did that, even though we can't read it, just to see what kind of another example of binary data looks like. Cool. I'm going to close that to make sure that I can open it in my program. Make sure I did paste it there. I'll just keep opening. Okay, I got people.dat tucked away safely. Moving on. Okay, we checked it. We're going to do some stuff. Keep getting information from the user and writing it to the file in binary mode. Cout. Enter person info. Cout. Name. Get line. Cin. Input. Nothing new there. What's the issue? Get line is undefined. Did I get all of my includes? IOStream, FStream, CString, CC type. We're using standard namespace. This happens, folks. Debugging on the fly. Let's add our while here, just to make sure that that's not somehow causing it. To upper response is equal to uppercase Y. Cin get line is undefined. Really? String? Maybe they forgot one. Because I don't see it. Okay, fine. Let's get line. All right, let's strcpy person.name input.cstr. So what are we doing here? person name. Okay. So what we're doing here, we have a person record or a person struct. We're going to get input from the user and take that input that's currently stored in input. Input is like the string that we're going to be using in all of our CNs and getLine and stuff like that, just as a temporary placeholder for data. And we're going to take that, convert it into a C string, and then stick it into person.name. So now person has a name. And we're going to continue in this fashion, like with age. C into person.age. cn.ignore, which, as the comment suggests, skip over the remaining new line. Cout address line 1. Get line cn input strcpy. Copy whatever we just grabbed for address line 1. Copy it into person.address1. Copy it from input. Good. Cout address line 2. And we'll get line. Like so. What is this complaining about? No suitable conversion for string to const. Oh, do we need to do? Yes, we sure do. CSTR, like so. We've got address 2. Now all we need is, let's see, we better copy it over. strcpy person.address2 input.cstr. Good. We got it copied. Now let's do the phone. get line cn input strcpy person.phone input.cstr. Now, people, this is the crux of the matter here. We've got a bunch of data. We've got now our person info struct is filled out. So we've got data stored in an info struct. Now we can finally do something with it. So we're going to say people.write reinterpret cast. Must have a pointer to char. Just a part of that syntax. What are we going to pass into that? We're going to pass the address of our person info struct and the size of person. That's pretty cool. We don't need to know how big a person is. We just say, hey, whatever the size of this thing is, use it. I don't care what size it is, but whatever it is, just do it. Now, cout, do you want to enter another cn response cn.ignore. Good deal. Once we're done with the do while, people.close, return 0. Let's see what their sample input is. Set a startup. This may be unsafe. Unsafe. Can I suppress that? Let's see, string copy underscore s. Well, you suggested it. Why not? Str copy. The joys of programming. Things deprecate, and we have to do other things that we may not completely understand why, but we do them and they work, and that's all we care about. Oh, what now? Oh, forget one? Yep. Okay, fine. We're going to add an underscore s to all of our str copies to make them safe. Beautiful. That's how it goes sometimes, people. And you don't always have to question it. All right, Charlie Baxter. Age something. 1 to 3. Fake street. Somewhereville instead of Esterville. I don't know. I don't feel like entering another. And supposedly it just wrote to that file. Okay. We'll close that. Let's go check out that file. Again, it's not going to mean much to us. Yeah, I can kind of see the data. Notice how it overrode the, I think it was Abraham Lincoln data that was here. You probably don't see the strength of this right away. Okay, I've got I know my data is kind of in this people.dat file, but what good is it? I mean, yeah, it was pretty easy to write all that person information to that file. Once I got the person info struct filled out, like this is all stuff we knew how to do, including the underscore s, wink, wink. We knew how to do that. That's pretty easy. We're just one by one getting information, getting data, filling out this struct. But then if we want to write it all to a file, I don't have to go and say person.name, write to a file, person.age, write to a file, person.address1, write, address2, write, phone, write. I don't have to do all that sort of stuff separately line by line. Instead, I can take my whole person struct and write it all to a file at once. That's pretty nice. I don't have to do all the data separately. I can do it all at once with people.write in binary mode and just specifying the size of the person that I want to write, and I'm good. But again, it is stored as binary. So if I just want to pop that file open and look at it, not going to make much sense to me. So that's where the next hands-on comes in, 1313, which we're going to do, to then take that binary file and read it in. Oops. Okay, include IOStream, include fstream. Okay, I think we have the same. Yeah, I'm going to copy over that same struct and the name size, all that good stuff. So keep in mind, really in a real life scenario, this would all be in one sort of file. It'd all be in one program, so I don't have to copy and paste my struct back, but just to keep things nice and modular for demonstration, I'm going to keep them separate and just copy and paste this info struct over. It is important that the info struct is the same between both programs. So here we go. I need my consts like so. Now inside of main, got my info person, jar response, fstream, PEO, people.dat, iOS in, iOS binary, if not people, and the one thing I do need to do, I'm going to do it right now, in fact, while I'm thinking about it, this is 1313. I need to open this in my File Explorer. I need to open my people.dat. I'm going to do a file save as on that. And I'm going to save it into my 1313 people.dat. Okay, so it's in both locations now. It does contain that 123 Fake Street address person. So I've got data in here to read in now. Labeled output, cout, here are the people in the file. Extra new line for emphasis. And this is, again, this is the cool part right here, to read in, not only to read in the people data, but to put it in a structure that's nice and organized and compact in a format that I can work with really easily in my code. This is all I have to do. People.read, reinterpret cast, char, pointer, address of person, size of my person. I need a comma there. In fact, let's put it on a second line. While not people.eof. And then I can just, I'm not going to type at all because it's a lot of typing. I can just print out that data line by line. But to actually read it in, to get the data from that binary file, which I don't understand, into my program, into a structured format that I do understand, is very easy. Once you have the data captured, you can write it all to a binary file with this single line, and you can read it in with this single line, and then how you deal with it in this while loop, that's just up to you. But that is really cool. I don't have to read in one piece of data one line at a time. I don't have to write it to the file one line at a time. There's a very special word that's used for this in computer programming. It's called serialization, where you're taking some kind of complex object, you're translating it into binary data that a computer understands, saving it somewhere, either saving it to memory or saving it to your computer's hard drive, like we're doing in this case. And then once you saved it out there, somewhere else, when you need it, you can retrieve it very, very easily. So you serialize the data, turn it into binary, then you deserialize the data, turn it from binary into some structure or format that your computer program understands that you can work with as a programmer. Sometimes the format that's used is binary. A lot of times you do binary serialization. Another format that's very, very popular these days is called JSON. JSON stands for JavaScript Object Notation. While binary is a data format that humans do not understand, at least very well, if you looked up JSON serialization, you would, if you looked at a JSON text file, In fact, let's look it up. Sample JSON file. You would notice that it's something that you probably can pretty much understand. First name, John, last name, Doe, age, blah, email, blah, courses, math, science, history. This is another format that you can use to serialize your data. And it's a common, standardized, open source format. Just like binary is, you can also use JSON to serialize and deserialize your data. It's a very, very common modern way to pass data around from program to program, from service to service. Very, very cool stuff. At least I think so. So we just did 13. Notes on structs written to files. So it must not contain pointers. So if you think about it, it makes sense. How am I going to write like a pointer to a file? I'm going to write a memory address? No, I don't think so. Since string objects use pointers in dynamic memory, structures to be written to a file must not contain any string objects. That's why we used the char array. Okay, because that string is a pointer in dynamic memory, we need to convert it to our char array. And just wrapping up the lesson here, not too terribly much to go. We'll skim through the rest of the hands-ons here. Random access files. So sequential access is what we've been working on. You start at the beginning of the file and go through the data in order to the end of the file. And to access the 100th entry in the file, you have to first go through 99 preceding entries. Not very fast. For 100 lines, that's not a big deal, but for 100,000 or 1,000,000 lines, it would be a big deal. And so using random access, you can access data in a file in any order where you can access the 100th entry directly. Here's kind of how you do it. Seek G. Hey, there's what that G is. Seek get and seek put. Get and put. Use with input, use with output, both used to go to a specific position in the file to read from it or put data to it. We already talked about the offset and the place. So the place is like where you're starting, and then the offset is from how many spaces or slots, I guess, from the place do you want to go. It's an integer specifying the number of bytes, not places. I should be more specific. Number of bytes to move from the place. And the starting point could be something like this. Beginning, current, or end. Here's an example. So sets the read position to 25 bytes after the beginning of the file. So start at the beginning of the file, move forward 25 bytes, and that's where you're going to seek G. Here, you're going to go 10 bytes before the current position. So wherever the current position is that you're reading or writing from, in this case putting, you're going to move back 10 bytes. So negative values are allowed. Let's check out 902. Program demonstrates the seek G. Okay, variable access the file, opens it up, letters.txt, gets the 5th byte from the beginning of the alphabet. Okay, starting at the beginning, move forward 5, get the character, byte 5 from the beginning, print it out. Similarly, get the 10th byte from the end. You can start at the end of the file, go back 10, get that character. Then, based on where you currently are, move 3 bytes forward, get the character, print it out, close it, return it. Here's the output, F, Q, and U. Oops, I think we started back on the previous page, actually. Program demonstrates the use of a structure variable to read a record of information. I love structs. If you can't tell, they're a nice compact way of organizing data. So we've got our info struct, we've got our function prototypes, we have a show record function and some kind of byte num function. Let's see what those do. Show rec just prints out the info record. This guy, the definition of function byte num, accepts an integer as its argument and returns the byte number in the file of the record whose number is passed to the argument. Very good. So we've got our person info. Try to open people.dat in input and binary mode. If you can't fail, skip forward and read the record. Read record 1 in the file. So here's record 1. Seek forward from the beginning the size of byte num with 1 passed into it. And just to remind ourselves what byte num does, returns the size of an info object times whatever the parameter is. So we passed in 1. So because we want the first record, we're going to take the size of our info struct times 1, which is just itself, and that's going to be our size. Like that's the part that we're starting at. Because we're starting at the first one, we're just passing in 1. Then we're going to deserialize, read it in, and show the rec. Now if we want to skip backwards, we're going to start at skip backwards and read record 0 in the file. Oh, I see. So IS beginning, pass in 0 to the byte num, get my position, read it in, show it, close it up, return. Here's a couple new ones I wasn't aware of. Random access information. Tellg member function returns the current byte position in the input file as a long. So like, where am I in the current file? Where am I in the file in terms of position? Well, tellg will tell me that. Tellp returns the current byte position and output as a long. So one is for input, one is for output. Opening a file for both input and output. A file can be opened for both simultaneously, supports updating a file, so reading data from file into memory, updating the data, and writing it back. We use fstring for that, as we've seen. Like if you're opening a grades.dat, you can input and output. Let's wrap up with a few more hands-ons, and we'll call it a lesson. So it sets up a file of bank inventory records. Again, we're working with our struct here. I presume we're going to have, 5 records. Got our I don't know why we can't just write out the word inventory. Anyway, it's got an array of chars called description of size, desk size, an int quantity, and a double price. So we're creating our first record here. Basically an empty one. Creating a file object and opening it up if it doesn't exist. Writing to it, now writing record blah, and we're using inventory.write. And similar syntax as we've seen before. Displays the contents of the inventory. So the previous one, let's double check that again. Yeah, the previous one wrote to the inventory. This one is reading from. I'll let you skim through it, but it's similar to what we've done so far. And then 910 allows the user to edit a specific record in the inventory. I would highly recommend you go through this one on your own. So in the world of computer programming, there's something called CRUD. C-R-U-D, and it stands for create, read, update, and delete. If you've ever used any like portal systems or even like worked with your own student portal, you can do these operations. You could do something like create a class in your schedule. You could read the classes that are in your schedule, like read only, view their details. You could update a class that's in your schedule, and you could potentially remove a class from your schedule. Those operations, create, read, update, and delete, are fundamental to most all computing systems. Those are 4 operations you almost always will support. We talked about an example on the web, your student portal, but just in a simple text-based desktop application, you would want to do these things too. And this is an example that would help you code something that would do that. So program allows the user to edit a specific record. So you could have a record of inventory data or a file full of inventory data, specify which record of inventory you want to edit, make the change, write it back to the file. This is a very, very practical, useful, hands-on example that I know we're 90 minutes in already, but I would very much recommend you guys check this one out on your own. This will tie together many of the concepts we've discussed so far. Similarly, there is a case study, Online Friendship Connections case study, that is not like graded or required, but if you're really wanting to be successful in this stuff out in the real world, highly recommend you take a look at the Friendship Connections case study on page 912. Again, this is going to reinforce the idea of serialization. This is a very, very powerful, useful technique used in real world computing all the time. I use it almost daily in my day job. Like, it's that foundational, that fundamental. We're always reading from and writing to different data sources via simple text files like we've been talking about in this chapter, or full-fledged relational databases like SQL Server. This stuff matters. So if you can understand this editing of the inventory file, this online friendship connections case study example, I would say you've got a win for this chapter, chapter 13. All right, look for the assignment to be posted soon if it's not already. And I will say thank you very much. We'll see you next time.